Alrighty, welcome everyone to yet another episode of the Boost Your Biology podcast. Today I'm joined in with a special guest, an expert in nutrition and metabolic health and a whole lot more. So I'm really honored and I'm really excited that Tommy Wood has joined me in today. So Tommy, thanks and welcome to the show.
Oh, thanks for having me.
Awesome. So maybe do you want to give my listeners a bit of a background into, your journey into nutrition and the things that you love doing today?
Yeah, sure. So I currently work in Seattle. I'm a research professor at the University of Washington. But I grew up in the UK, as you can probably tell from my accent. I did my undergraduate degree at the University of Cambridge in biochemistry. Then I went to medical school at the University of Oxford. And while I was at medical school, I got really interested in various aspects of athletic performance. I was an athlete myself. I came to that late in life, like essentially not until my 20s. I was a biscuit eating, TV watching layabout until then. But then particularly started rowing, coaching rowing, sort of found CrossFit and various other things, and was particularly interested in various nutritional strategies to try and improve performance in the athletes that I was coaching. And then I also spent a good deal of time trying to dissect the potential root causes of multiple sclerosis, because I have a stepbrother who was diagnosed with multiple sclerosis. He's the same age as me. And we basically dug into well over 1,000 research papers and just said, assuming we know nothing to begin with and everything is potentially relevant, what are the potential things that factor into risk of both the incidence and progression of multiple sclerosis? And all kinds of interesting stuff falls out in terms of chronic infections and molecular mimicry and toxic exposures and genetics and vitamin D and nutrition and all this kind of stuff. And that kind of was my first principles introduction to some of these things that we might call functional or integrative medicine. And then when I started my PhD, so I finished my medical degree, worked in London as a junior doctor for a couple of years, and then started a PhD in physiology and neuroscience. And then that sort of gave me time to dig back into the research again on all this kind of stuff. So I have two parallel tracks. One is where I research brain injury, particularly neonatal brain injury, but also pediatric and adolescent traumatic brain injury. In the lab in animal models. And then on the side, I've continued to work with various athletes and then also people with various chronic health conditions, be those gut related, metabolic health related. And so those are kind of my parallel tracks. And I spend as much time as I can sort of trying to integrate those things. How do various environmental and lifestyle exposures affect both the development and susceptibility of our brain to injury? How do those things affect performance? How do we keep our brains working as well as possible for as long as possible? And obviously, one of the biggest things you mentioned earlier, that's this kind of this is essentially endemic now is metabolic syndrome or various aspects of metabolic disease. So I spend a lot of time thinking about that and trying to figure out ways to help as many people as possible improve their metabolic health, which is essentially going to keep us alive for as long as possible. And that could be susceptibility to various viral infections, or it could be dementia, Alzheimer's disease, heart disease, all that kind of stuff. It's essentially all connected in various ways.
Awesome. So let's sort of delve into more in the realm of sort of metabolic health and insulin resistance, and let's sort of discuss some of the leading theories of insulin resistance, because I know there's a few theories and a few mechanisms at play. So do you want to expand on that?
Sure. So insulin resistance is kind of been touted as the root cause of most modern chronic disease. And so those that, like we talked about, certainly type 2 diabetes is essentially pathognomonic of type 2 diabetes is systemic severe insulin resistance. But it's also associated with obesity, heart disease, cognitive decline, certain cancers. And I don't think that saying insulin resistance is the root cause is correct, because insulin resistance doesn't just happen, right? Insulin resistance itself has a root cause. But it does kind of tie together, or it's part of the physiological picture of essentially all these modern chronic diseases. And when we think about what insulin resistance is, I think it's important to think about, how we might be measuring it, essentially. And there are kind of increasingly complex ways to measure it. So the simplest way might be you measure your fasting glucose and your fasting insulin, and you see how much circulating insulin do you need to keep your glucose at a certain level. And then there are things like the HOMA-IR that you can calculate from that. The next step up might be to look at something like an oral glucose tolerance test. So you give somebody a boatload of glucose to drink, and then you see how much their blood glucose rises over time. And ideally, you'd also do insulin at the same time. That's something that people might call a Kraft assay. And again, you see like how much insulin do you need to keep your glucose under control. The gold standard is something called a hyperinsulinemic euglycemic clamp, where basically people stick a needle in your arm and they pump you full of glucose and insulin and see how much extra glucose they can shove into your cells with that insulin. And so people who can take less extra glucose in their cells for a given amount of insulin, are labeled insulin resistant. The problem is that the job of insulin is not to shove glucose into cells, and this is what people like fundamentally misunderstand about insulin. And I think the reason why people think that this is the case is because we discovered insulin in the setting of type 1 diabetes, where people can't make their own insulin and we have to give it exogenously. We have to inject it into the periphery, and then it does go and it does help shove glucose into cells, because you need some small amount of basal insulin just to have the cells open for glucose. But what insulin should do in the sort of healthy body with a functioning pancreas is, the first thing it does is it gets released from the beta cells in the pancreas, and then it reduces, or it stops the secretion of glucagon, which is kind of its antagonist, also released by the pancreas. Then it goes to the liver and it tells the liver to stop making its own glucose. It shuts down gluconeogenesis. Then it goes out into the body. And the main thing that it does is it stops the breakdown of protein from skeletal muscle, proteolysis, and it stops the breakdown of fat tissue, lipolysis. It doesn't really do much for the uptake of any of these things into cells, including glucose, except at very, very high doses. So the main thing that insulin does is it stops the breakdown of fat tissue and muscle, because those things are always ready to be released so that they can go to the liver to make glucose, just so you always have some glucose, floating around. So when we test for insulin resistance by shoving people with loads of extra insulin and glucose, we're not really testing the normal functions of insulin, and it is definitely super physiological. And when people are insulin resistant, so if you're type 2 diabetic, your muscles are already taking up more glucose than somebody who's not type 2 diabetic. There's more glucose floating around because the liver's making it when it shouldn't, and your muscles are already sucking up as much as they can. So when you then ask it to take up more, it just doesn't have the capacity. So we've kind of got the whole idea of what insulin does backwards. And then you might think, well, what is it that stops the cells listening to the signal of insulin? That's essentially what insulin resistance is, right? For a given amount of insulin, you get less of the downstream signal. And, we spent a lot of time. So the same way we kind of try to decipher the root causes of multiple sclerosis, we try to do the same things for insulin resistance. And three main things kind of pop up again and again. And they are oxidative stress, particularly in the mitochondria, and how those signal to the insulin receptor. Inflammation, and that can come from many different things. It could be an autoimmune disease. It could be endotoxins from the gut. It could be some other kind of infection. And then the last thing is energy toxicity. It's basically that cell already has too much energy in it. And when that happens, then it says, hang on a second, no more. And it tries to shut down the signal from insulin. So what causes insulin resistance is some confluence of those three things, in my opinion. And then, from there, you just, in an individual, you might say, well, let's figure out which of those things are the most important for you, and try and remove those, be it oxidative stress, inflammation, or energy toxicity. And those actually intersect. And for most people, it's energy toxicity. You have eaten too much, your fat cells are too full, they have become insulin resistant, and then all this downstream stuff happens. Insulin doesn't stop your fat breaking down. The glycerol from your fat goes to the liver, it becomes glucose. Most of the glucose in people who are type 2 diabetic comes from their liver making it, not from the diet. So the liver is inappropriately making it because your tissues are breaking down protein, breaking down fat. Those precursors go into the liver, making glucose. And so then you need to find some way to improve usually the health of your fat cells. It could be your skeletal muscle. You can be insulin resistant primarily in your muscle. That's mainly going to be if you're really sedentary and in some kind of inflammatory state. So that can happen with if you're immobilized, certain cancers, that can certainly happen. But basically, your fat cells being more full than they want to be, that's essentially the main source of insulin resistance in the majority of people.
Right.
That's a long answer to your short question.
That's all good. So, Tommy, do you want to explore a little bit about, I guess, how certain dietary interventions, and I guess the big one is like the high fat, high sugar diet, and you know, because I know the carnivore diet's trending very much at the moment. I listened to your episode with Paul Saladino, which was awesome. But I want to sort of discuss more about that, you know, high sugar, high fat combination. And another question I also had was in relation to fasting insulin. Now, I've always been curious to know how quickly that can fluctuate. Like, let's say I go on a very, very high carb diet, like let's say 400, 500 grams of carbs a day. And am I going to see changes in that fasting insulin relatively quickly, or is that going to take a bit of time?
Yeah. So to answer your second question first, if you go on a high carbohydrate diet where everything else is good, you're in good health, you're not in caloric surplus, your fasting insulin probably won't go up much at all. It certainly shouldn't. There are, you know, if we look at some of the hunter-gatherer data, that's some of the best that we have. So if you look at the Gatavan data, these guys eat sometimes 80, 90% of their calories from sweet potatoes, mainly carbohydrates. Their fasting insulin is 2, 3, super low. So the carbohydrates in your diet don't necessarily translate to having higher fasting insulin. That's going to be a downstream effect of some kind of systemic insulin system problem, which again goes to those other things that we talked about. In terms of, so the high fat, high sugar diet, the Western diet, the cheesecake diet, is essentially the best way to make people insulin resistant. But it does require a caloric surplus, essentially. And there may be aspects of that diet that in some people have that cause an inflammatory response. So that's certainly possible. I don't think it's common, but it's definitely possible, right? I've worked with lots of different people with various dietary intolerances. But if you overfeed people a Western diet, like Big Macs and milkshakes and cheesecakes, you can make them insulin resistant in a couple of days. And they've done these studies where basically they overfeed them maybe 2,000 or 3,000 calories a day. And then they also do these hyper insulinic euglycemic clamps every day to check their insulin sensitivity. And then also at the same time, they're also shoving extra calories into these guys, doing that as well as the Big Macs, just the process of testing for insulin resistance. And you basically see their home IR, their fasting insulin, just like their glucose stays the same, but their insulin just goes up day by day by day, right? And then other things, so oxidative stress dramatically increases day by day by day. So you can do this stuff really quickly, but the caloric surplus is generally required. And the reason why these diets are problematic, or one of the reasons why these diets are problematic, is because when you dissociate carbohydrates and fats from their natural state, I'll call them, they interfere with the normal hormonal signaling. So you'll get larger insulin responses. And you'll get, changes in incretins and other satiety hormones, such that you get much less satiety for a given number of calories. And we're actually very bad at sensing the number of calories that we're eating if the food is more than 1.5 calorie per gram in terms of energy density. So because these foods are so energy dense, and because they hijack physiology, they make it much easier to overeat. Now, if it fits your macros person, and you're happy to count your calories accurately, you can eat these foods, and those guys are also probably going to be fairly young and fit and active, so they can be absolutely fine metabolically. But the issue is that it's very easy to overeat these things because of the way they hijack or bypass our normal satiety mechanisms.
Right. You mentioned something about how glucose actually stays the same. And I know this is a common issue with, like, I guess, people going to a regular doctor and getting their blood sugars taken, their blood sugars within the range. But ultimately, what's happening there? So, like, with the blood sugars staying within range, but what's happening behind the scenes?
Yeah, so in these guys, and so these guys, you know, it's only so this particular study I'm thinking of, where they overfed these guys on a Western diet. As you try and stuff more and more energy into the cells, so this is particularly going to end up in fat cells. They are, and then you continue to do that, they are going to become insulin resistant, right? The energy toxicity is there. They already have enough energy, but you're trying to shove in more. So then, in order to stop the fat tissue breakdown and protein breakdown in the muscles, which then go to the liver to be precursors for glucose via gluconeogenesis. In order to so you need more insulin to have the same anti-catabolic effect. So the glucose stays the same because gluconeogenesis is still shut down, but it requires more insulin to do that job. So that's why you see fasting insulin climbing up, but glucose staying the same. And that's kind of like the early stages. And it, you know, in this study, it's happening quite acutely, but that's the early stages of insulin resistance where glucose stays the same, and it's very tightly regulated, right? Your body wants a certain amount of glucose, and it's ready to make it, right? So as soon as insulin drops, you'll start to break down muscle tissue, you'll start to break down fat tissue to make sure that that energy is available for the, you know, for the brain particularly, but also, you know, all the other organs. But it also, you know, glucose is toxic in high doses. So you also try, you know, it's very tightly regulated. So you'll keep that glucose as tight as possible for as long as possible, but insulin will climb in order to do that. Then eventually, you know, those systems become overwhelmed and glucose starts to increase. One potential problem with normal reference ranges, and it's certainly the case with glucose and also many of the things that you might get tested at a doctor, is that you're comparing yourself to an average population. And in general, the population on average is sick, you know, particularly, I mean, the US, I don't think that Australia is much better. And, you know, on average, 80 to 90% of people have some of the symptoms of or signs of metabolic syndrome, or they're kind of on the way to that. So when you're then comparing yourself to, and when you make a normal range, you basically take the average and 2 standard deviations either side, so to fit a normal bell curve, and then you say if you're in that middle 95% of the population, you're normal. But when everybody on average is sick, then that normal is maybe not that normal. It's maybe quite abnormal. And so I think, you know, the best kind of long-term outcome health data seems to be if people keep their blood sugar between 80 and 90 milligrams per deciliter, basically between 4 and 5 roughly millimolar. And if you're in that range, you're probably going to be in pretty good shape. As soon as it starts to creep over 5, then you start to see increases in risk of all-cause mortality, death, heart disease, that kind of stuff.
Right. So let's sort of switch it over into the athletic performance realm, because I mean I've got a pretty extensive background in played soccer for many years, and right now I'm training pretty hard and trying to put on some muscle and things like that. So let's sort of discuss. I really want to explore what you've researched in the realm of the carnivore diet and how they're able to. I mean, are they able to maintain a high intensity efforts and things like that?
Yeah, that's a great question. So carnivore is kind of new on the scene relatively, you know, maybe keto was kind of like the precursor. But I think they are fundamentally different in one important way, which is the amount of protein that you're going to consume. Generally, you know, most people who are on a ketogenic diet, and if you're on a ketogenic diet for some kind of neurological disorder, or, you know, you need ketones at a certain level for therapeutic reasons like brain cancer or something, then, you know, it's important to track ketones. But people often track ketones, and therefore, because they think it's better to have more ketones, they reduce their protein intake, which does suppress ketone levels. But I think that's going to be detrimental, particularly in people who are trying to maintain or gain lean mass, which, to be honest, should be most of us. You know, muscle mass is just probably one of the most important things for long-term health. Um, and so if you eat enough protein, then you'll basically make extra glucose if you need it. And then that protein will increase insulin. It will also increase glucagon, but it will increase insulin, which will then help stop the breakdown of muscle tissue, which is what you need. So because you're removing all the carbohydrates from the diet, you need extra protein to provide that anti-catabolic signal. And then also potentially as a precursor for glucose. So when athletes go on low carbohydrate diets, in order to maintain their muscle mass, I think they need to increase their protein intake, which will reduce their ketone levels. But for most people, the absolute level of their ketones doesn't matter as much unless they're treating a specific disease. So in terms of the highest level of athletic performance, we don't really know how those guys do on very low carbohydrate diets, be that keto or higher protein, low carb, something akin to a carnivore type diet, just because there's not many of them who are really willing to try it out. And maybe there's a chunk of the off season where you'd be willing to give it a go, but there's just not that many people, and therefore there's not enough to create a study within a specific sport. So we don't really know. With the athletes that I've worked with and myself, and I've tested all these various things. If I go on a regular ketogenic diet, so high fat, moderate protein, I can't maintain muscle mass and I can't maintain performance. There just isn't enough protein in the system. There isn't enough insulin signaling, I think, to maintain my mass. But when I tried out carnivore, just to see what it was like, I was eating a lot more protein, like 250, 300 grams of protein a day. And I did fine. I was doing interval sprints on the rower and the air dyne. I was doing high volume weightlifting, squats and deadlifts and all that kind of stuff. And actually, I saw very little deficit in my performance. In fact, none really. So if people are going to try it, I can't say anything about the uppermost levels of performance because there isn't really good data on that. For the average person, which probably includes you and me, even though we're very active and training pretty hard, I think you'll probably perform just fine as long as you increase your protein intake.
Yeah. I want to touch on, there's a lot of myths around protein in general, and I want to discuss overfeeding on macronutrients. So, for example, I know you've done a lot of research in that realm and looking at, I guess, what happens when we overfeed someone with protein. And I know that because I've seen a particular study, I think it was in obese women, where they overfed them with protein, but they actually lost weight. So do you want to discuss the myths around excess protein?
Yeah, so protein has become, right, we cycle through which macronutrient we're going to choose to demonize at any given time point, right? It was fat, then it became carbs, now it's protein. And the reason why it's demonized is because it's thought to increase mTOR signaling, which is associated with cancers and in people who have like genetic deficits in that system, like IGF-1 mutants. Those these people are very short, but they live a very long time. And there's been some terrible epidemiological studies looking at protein intake and cancers and things like that. But I mean, they're essentially just junk science. So I try not to pay too much attention to them. And actually things like IGF-1 are super important. So if you look at all-cause mortality and you look at IGF-1, it's a perfect U-shaped curve. So if you have high IGF-1, yes, that's associated with certain cancers, maybe heart disease. But if it's low, then that's associated with sarcopenia, hip fractures, and that's what kills people. Once you get to like 75, 80, falling down, fracturing a hip, and then dying of pneumonia in hospital, like that's what kills people. So having low IGF-1 is not a good thing, particularly as you get older. So you basically just want to be average. So if anybody's measuring their IGF-1 levels, then as long as you're somewhere in the middle, in the middle chunk of the range, you're in good shape. And with the overfeeding of protein, protein has a very high thermic effect of food. So basically, like 20 to 30% of those calories are lost to heat. So even though technically you guys work in kilojoules, don't you? But so in kilocalories, right? You have 4 roughly per gram of carbohydrate and 4 per gram of protein. But actually, it doesn't quite translate into that. You'll get fewer calories out of the same amount of protein. So if you're just calculating them that way, then you can overfeed and you'll just ramp up your metabolic rate. And you could even lose weight even though you're supposed to be hypercaloric. The same thing does happen with carbs. So if you keep protein and fat intake relatively low, so fat intake relatively low, protein kind of moderate. If you overfeed people with carbohydrate, they will also ramp up their metabolism to try and burn off those extra carbs. And that, most people would think that if you're in the low carb sphere, if you overeat carbs, it immediately gets turned into fat and stored. But that's not actually true. Most of the fat on your body is fat that you ate. And so if you overeat with carbs, you'll also ramp up metabolism to try and burn it off. But it doesn't happen with fat. So if you overfeed by the same amount of fat, you don't increase your metabolism, and then that fat's more likely to get stored. Now, that doesn't mean that fat necessarily makes you fat, right? You still require a caloric surplus, however you calculate that. But the effect of the different macronutrients does have a different effect on our metabolism, and then, what the net amount of calories that are available are.
Awesome. So, Tommy, I want to sort of explore a little bit on, I guess, understanding. We're going to segue into muscle building. So I really want to focus on building muscle, things like that. So let's have a look at, I guess, the discussion around being in a caloric surplus to build muscle. So let's look at, is it possible to build muscle even though you hit your protein requirements, but you're in a caloric deficit?
Yes, it is possible, and there isn't great data on it. More and more is coming, but the studies that exist so far, and then if you do talk to people who sort of exist in this sphere, it is possible, and the reason it's possible if you have a decent amount of adipose to make up the difference, right? So when you lose weight, rather than the calories come from your stores, your adipose tissue, your fat tissue, rather than coming from the diet. So if as long as the deficit isn't too large and you have adequate protein, yes, you can use some of your fat tissue as like metabolic fuel, and then also stimulate muscle growth. Is that going to be the optimal way? If you want to grow the maximum amount of muscle, that's not the way to do it. But you can. There's certainly enough data to say that if it's done properly, you can decrease fat tissue and increase muscle tissue at the same time.
Right. And let's sort of discuss a bit on the anti-catabolic nature of insulin. I know you mentioned before that it is very anti-catabolic. I know there's a lot of bodybuilders that actually inject insulin for that performance enhancing effect, that glucose enhancing glucose uptake and things like that. So is that a common misconception around like insulin? Not many people are aware that it's anti-catabolic.
Yeah, so most people think that insulin is anabolic, right? It directly stimulates the growth of tissues, including muscle tissue. And if you give it in super physiological doses, right? So if you're a bodybuilder and you're taking huge amounts and then also making sure you get enough carbohydrates to cover the drop in glucose, right? Because there've certainly plenty of bodybuilders have come a cropper, like they've injected a boatload of insulin and just haven't had enough carbohydrate. And, that can be super dangerous, right? You become hypoglycemic and you can seize and go into a coma and all this like really bad stuff. So at very large doses, it may stimulate muscle growth. But in most normal people, like after meals, even like in clamps, if you're infusing people with insulin and amino acids, what determines whether those amino acids get turned into muscle tissue is not the level of insulin, it's the availability of those amino acids. So amino acid availability is much more important for muscle growth than insulin itself, as long as you have just enough, right, to prevent the breakdown. And so for most tissues, the way I think about it is that then it could be your muscle, it could be your fat tissue. They're like a bathtub, right? So the bath fills at a fairly, like the tap is always on at a fairly constant rate. That's basically determined by the availability of either the fatty acids or the amino acids. And so insulin doesn't really regulate the tap. It regulates the plug. So it stops it coming out the other end. So it stops the breakdown of fat tissue, it stops the breakdown of muscle tissue, but the uptake is not stimulated, like the actual growth isn't stimulated. So you might get net growth, right? Because you put the plug in, right? If you put the plug in, the bath fills up. But it's not because you've turned the tap on more, it's because you put the plug in. Does that make sense? Like, I think it's really important to know like where it's acting. So then if you want insulin to stimulate muscle growth, you're going to have to inject a whole load of it, way more than you could normally make. And so does, do people who inject insulin for muscle growth see a benefit from it? I don't think we really know because it hasn't been studied, but the physiology will say you would need really large doses. And then even then, the effect is probably going to be relatively small compared to other things that you might do.
Right. So what about, I know you've delved into various supplements and nutraceuticals, and I know you've probably experimented with them personally and things like that. I know I've played around with mega dosing certain vitamins, things like just to see fluctuations in my blood sugar, and I'm just a typical biohacker in that sense. But let's have a look into, I guess, some interventions like nutraceutical or herbal or vitamin-like interventions or other compounds that can help with increasing one's insulin sensitivity.
So I think this is a bit of a double-edged sword, and maybe more of one than people realize. So in its own separate category, maybe we'll address first is metformin, which is the kind of the new darling of the longevity sphere. And they've just started the TAME trial over here in healthy older adults. So they're going to give them metformin and see, the incidence of various diseases and also all-cause mortality. And metformin in animal models, does seem to increase longevity. It's been replicated in multiple labs, mainly in mice. Now the problem is that, and then there's the other bit, which is that if you look, there's an observational study where you look at people with type 1 diabetics who take metformin, and you compare them to people of a similar age who don't have type 2 diabetes and therefore are not taking metformin. Those who are type 2 diabetic taking metformin may live longer and have better health, which is just like crazy. However, there were 2 recent studies that gave metformin to healthy older people and then looked at how they responded to exercise. So there's one that looked at aerobic exercise and one that looked at resistance training. And on average, metformin seems to blunt the response to exercise because it functions through the AMPK kind of nutrient sensing part, which is also stimulated by exercise, and it seems to interfere with it. So the smart money is on people who want to live a healthy, active lifestyle and benefit from it should not take metformin for longevity. However, if you're going to be type 2 diabetic and insulin resistant and you don't want to exercise, take metformin, right? Because it's very likely that you're going to live longer. So you'll be in one group or the other. But healthy people who are active, training hard, I don't think right now should take metformin. Now, in those studies, there were some people who still responded to the exercise. So we'll get to a point maybe where we figure out who's a responder, who's a non-responder, and the best ways to track that. But right now, I would say I don't think it's worth a healthy, active person taking metformin for longevity reasons or insulin sensitivity reasons. Then if you look at other things like, there's been, bitter melon, cinnamon, chromium picolinate, all these things have been shown to decrease blood glucose responses to meals or improve insulin sensitivity. I think there is potentially some use for those in the short term because it might reduce the amount of glucose that you have circulating, which is, glucose in itself, when it's circulating, is toxic. We don't want too much of it. However, if you're insulin resistant, you're in a state where your cells are saying, I don't want any more energy, right? So if you're increasing insulin sensitivity in that setting, you are then stuffing more energy into cells that have already said, I don't want any more. So you could create some downstream problems by increasing the energy load of those cells that are essentially already energy overloaded. So your blood sugar will look better and you'll feel better about that. And maybe there's a place for that. But in general, what you need to do is figure out where the insulin resistance is coming from and deal with that first. And there are loads of other things that I think that you could do that are more important. So if you go for a walk around meals, that's going to have a much bigger effect on your blood sugar than taking bitter melon or cinnamon. If you sleep properly, again, if you're moving frequently, if you eat your food in a different order, right? You eat your salad or your vegetable, and then you eat your protein, and then you eat your carbohydrates last, that has quite a significant effect on the glycemic effect of that meal. Or if in the short term, maybe you need to eliminate carbohydrates so you don't get big jumps in blood sugar, although not essential to reverse insulin resistance. You don't need to go low carb. So I think all of those things are super interesting, but just because of the way insulin resistance works, I do worry about the downstream effects of, yes, your blood sugar will be better, but have you done that at the expense of the health of the cells that you're then shoving that glucose into?
Interesting. So, Tommy, I want to look at a little bit on thyroid dysfunction, and I guess we're talking about is there an issue downstream with the ability to utilize that energy? And so, curious to know if you've looked into more around thyroid dysfunction or just some sort of mitochondrial dysfunction in the cell that's compromising energy, like the ability to actually burn the energy.
What do you have like a particular context in mind?
In potentially like a hypothyroid condition, like what's happening there?
Yeah, so obviously that can come from multiple areas, but I mean the most common is Hashimoto's thyroiditis. Most common again in middle-aged women, and then for whatever reason you've raised some kind of autoimmune response to your thyroid. You make less thyroid hormone. There are other things like if you have very high levels of systemic inflammation, and that's really going to take like a significant infection or very high levels of circulating cortisol, at least in the short term, that can cause this weird switch in terms of how thyroid is metabolized. So the brain sees enough thyroid hormone and doesn't ask for any more, but the peripheral body sees less and more of it gets converted to reverse T3. And so you're like peripherally hypothyroid, but your brain thinks you're getting enough. So there's kind of like a disconnect. That can certainly happen. But again, it's not the most common cause. And so in that setting, right, thyroid hormone is essentially what sets your metabolism. And to some degree, that is also signaled by insulin and carbohydrates, the amount that, how thyroid hormone works and the effect it has on your metabolism. So when you are hypothyroid, your metabolic rate is decreased. And so you have a lower basal metabolic rate, you're more likely to gain weight. It's going to be harder to lose weight. It doesn't mean you can't, but ideally you would get some replacement as necessary. But thyroid is essentially one of the major thermostats for your metabolic rate. So then the downstream effect is the amount of calories you need and how easy it is to gain weight for a certain caloric intake.
Interesting. So what about exploring a little bit in the realm of fasting? Have you done much like personal experimentation with implementing fasting at all?
Yeah, so I've kind of played with various aspects of it. I'm definitely a time restricted eating on the earlier side kind of person. That fits very well for me. So I eat in maybe usually like a 9-hour window from 9 to 6 p.m. I try and front load my calories earlier in the day. There are studies that suggest that more calories earlier in the day are associated with better weight maintenance, better metabolic health. The effect is quite small. So like, does it really, like, is it the thing that most people should be worrying about? No, absolutely not. Like if it's a stressor for you to try and eat most of your food early in the day, and then you have to miss dinner with your family because you're trying to have a short feeding window, right? All of that is going to be much worse for your health than worrying about exactly when you're consuming your calories. But there's maybe a slight benefit there. And I definitely like it because it gives me like a 3-hour window before I go to bed. And I sleep better because I'm not sleeping on a full stomach. And there's definitely some data to support that as well. So then from there, I've done like 1 day, 2 day, 3 day fasts just to try it out. I will say that when you look at data, so like when you look at animal data on things like intermittent fasting, caloric restriction, there seems to be, and especially if you do it not in a very specific strain of mouse, so or rodent, and most rodent studies are very controlled. Like you have an inbred, very specific population. They're all very, very similar, and you see an effect. If you then look across all the different types of rats and mice, or you look at outbreds like wild mice, and caloric restriction is probably best understood in this, but then if you calorically restrict just any mouse, right? It's not some very highly specific strain of mouse. About a third will live longer, a third you'll see no effect, and a third will live shorter. Particularly if you caloric restrict earlier in life, it may be more beneficial later in life. And I think intermittent fasting is going to have a similar effect. So in some people, it may well be beneficial, but I think there's going to be a good chunk of the population where it's just not something that's worth really worrying about. And there are all these other things that I think are going to be much more important. Total caloric intake and the quality of your food, sleep, social connection, movement. And when people talk about intermittent fasting, particularly prolonged fast, right, 2-3 days, they're like, you're going to increase autophagy. So, you're going to increase the breakdown of sort of damaged proteins and damaged organelles in the cells. But there's really no good data on this in humans, right? So a lot of it is extrapolated from mouse data, which again, if you look at one study and one strain of mouse, you may see the effect that you like. But if you repeated that experiment in a different mouse, you wouldn't see that. And nobody talks about that. And there were some recent studies where they fast humans for 2 or 3 days, and they look at markers of autophagy in white blood cells, circulating in the blood. And it's not even that they're looking at the proteins themselves; they're looking at the mRNA, which is like the signal to make the protein. So, like in one subset in the blood, there's the signal to make a protein that's associated with autophagy, and those things go up after 3 days of fasting. Is that good? I don't know. Right? Nobody knows that, but somebody will use that to tell you that fasting for 3 days is good for you and it upregulates autophagy. But in reality, we really don't understand it nearly as well as people think we do. And if you want to upregulate autophagy, at least in muscle tissue, the best thing to do is aerobic exercise. Autophagy is upregulated very quickly. Like a 30-minute run will increase autophagy far more than a 24-hour fast. So I think this is kind of like a super new thing. I think it's important. I don't think everybody needs to do it. I think there are things that are much more important, and there's just a lot that we need to. There's a lot that we need to learn, and all that other stuff I talked about earlier. At this stage, I think is much more important, and I see a lot of people stressing their bodies by fasting. And again, so people who end up working with me have usually tried everything. And they've read every blog and they've listened to every podcast, and they're reading papers, and you try and stack some of this stuff together, and it can become really problematic, particularly if you have a performance goal. Intermittent fasting in athletes is mainly just going to lead to a caloric deficit, which is going to lead to thyroid issues, hormone issues, sleep issues, recovery issues, and that's where I see a big problem. I've had athletes come who they're training 20 hours a week, but they're also low carb, low protein, intermittent fasting, and they're a complete mess, like, to put it sort of simply, just because they're not eating enough. So they're, particularly when it comes to athletic performance, like eating enough food is one of the most important things. And there's also the other side of that, just to kind of argue with myself. The other side of that is that for some athletic goals, if you want to perform in strongman, right? I do that because I really enjoy strongman, and I'm going to try and do some strongman competitions next year just for fun. Like, I'll get my ass kicked, but that's fine. You're going to have to eat 7,000 calories a day, right? And you're going to have to gain a load of weight. And you're probably, if you want to be really good, you're going to have to be pretty fat, and you're going to have to take a lot of steroids. None of that is good for your health, right? And nobody's pretending that it is. But if you want to perform, if you want to be as strong as possible, you need to do that. So at some point, there may be a bit of a balance between, like, what do I need to perform now versus what do I want my long-term health to be. And that's like an important ongoing conversation that you may have to have. But for most athletes who are training hard, training an hour or two a day, eating enough food is far more important than how much time you spend fasting. And I'd say the latter is potentially detrimental.
Yeah, I like how you brought up the sort of like that interplay between athletic performance versus longevity, that trade-off. That's something that I've always, like, personally, I've always been like, right, what do I want to focus on today? Am I focusing on longevity, or do I want to just train super hard and build as much muscle as I can? And you're right. Yeah. In that sense, it's like it's a trade-off, and you're going to have to just be okay with, all right, well, I'm setting that as my goal. I want to build muscle. I want to get strong. I might have to become slightly insulin resistant for a few weeks or whatever. But then ultimately just understanding that that's part of the process, I guess.
Yeah, exactly, and I think that's fine, right? Everybody has their own goal, right? Not everybody wants to or has to live forever. And I would, like me personally, I would much rather look good, be strong, and just like live long, drop dead, right? 85, heart attack. I think that's a great way to go. And just be fully functional until that point. That's much more important to me than living a long time but being, emaciated and unhappy and like bedbound during that time period because you didn't invest in your muscle mass before then, right? But that's my personal choice. Other people will have a different choice, and that's fine.
Exactly. And the other point you brought up earlier on was the importance of having that muscle mass and how that's a huge determinant of overall longevity, right? Like is that something you've seen? Like it's muscle mass that is really a huge dictator of longevity.
Yeah, and all the things that I care about in terms of longevity. So yes, muscle mass itself predicts or is an important predictor of all-cause mortality, also most chronic diseases. And like muscle mass and muscle strength have potentially different effects, right? So muscle mass may help more with things like glucose regulation just because you've got more tissue to soak up that glucose, right? That's important. But then strength is also going to be important because, your type 2 muscle fibers, 2A muscle fibers, like when you stumble and trip, you want those fast twitch muscle fibers to stop you falling over and breaking that hip. So then strength is also important. And when you and you can look at this, leg strength, obviously, but grip strength is probably the easiest to test and is a really nice predictor of muscle mass and mortality. That's an easy thing to look at. But then also, if you look at the size and function of the brain, so those people who have higher muscle mass have better measures of cognition. They have bigger brains, and again, maybe that's there's multiple potential reasons for that. So it could be because when you exercise, you release all these kinds of things that reduce inflammation, stimulate neurotrophic factors, so it can stimulate plasticity and neuroplasticity. The first time we really learned that the adult brain, like the old brain, can grow new cells was in a trial of exercise. They just had people walk for 45 minutes 3 times a week, and their hippocampi grew, right? Crazy. Like it's just a little bit of movement does that. And then the other side of that is all, again, it's a repository for glucose. It decreases inflammation. The act of movement is anti-inflammatory, which again is going to be super important for all those kinds of things. So through multiple mechanisms, having muscle mass and using it, basically decreases the risk of everything. Like, yep. It's as simple as that.
Of course. Tommy, we're nearing the end of the show, so I want to just wrap up, just by delving into some areas that you sort of seem to be, focusing on, like in terms of the next maybe 5 to 10 years. Where are you spending majority of your energy and research?
Yeah, so there are a few things that I'm really interested in. I mentioned right at the beginning that most of my research is in neonatal brain injury. And one thing that I'm really interested in is how early injuries to the brain. So say if you're born prematurely, and kids who are born prematurely, and the more prematurely they're born, the increased risk they have of various neurodevelopmental disorders. And so does some kind of early life insult affect your susceptibility to a later brain injury? So if you then get in a car crash, or you play soccer and you get a concussion, if you have some kind of early life change or problem or injury, does that increase or does it change your later risk or like of Alzheimer's disease? So you only have one brain, and things that happen right at the beginning of life will determine like what happens for the rest of your life. So how those things interact is very interesting to me. Also, how various aspects of the diet affect that. So the fats in the diet, glycemic or glucose variability, how do those affect the susceptibility of the brain to injury? So that's something that we're potentially looking at both in clinical cohorts of babies, but also looking at in the lab. And then also we talked about traumatic brain injury and ways to treat that. What are the really, first of all, are there like some brand new therapies that we can look at, and that's something that we are working with, particularly exogenous ketones is something that I'm looking at quite extensively, basically injuries across the lifespan. But then also, what can we do just in the any person who gets a concussion or gets a brain injury? And I think there's a lot of important stuff there in terms of fatty acids, glucose regulation, creatine can be super important for protecting the brain. So those are like the main. So most of them are brain centric, and then trying to find the best ways to keep our brains as healthy as possible across our entire lives, and then also intervene as necessary if we get an injury. And I think the things that are required to build a healthy brain from a nutrient standpoint or a precursor standpoint are ketones and certain omega-3 fats. So they're super important for building a healthy brain. So if you're then trying to repair a brain, I think those things are also important. And I think those are kind of not as well utilized as they could be in adult brain injuries. So kind of tying those things together is where I'll spend most of my energies.
Fascinating, man. I'm looking forward to keeping up to date with your Twitter and your other socials as well. So do you want to give my listeners a chance to find you and your services and your things that you offer?
Yeah, sure. So follow me on Instagram at Dr. Tommy Wood. That's probably where I don't spend a lot of time on social, but that's where you can find me. I'm at Dr. Ragnar on Twitter. Ragnar is my middle name. And it's also my website. So drragnar.com. It's super out of date, but one day like once a year it gets updated. So people can also check back there. And through my website, there is it's probably easiest, like people can, I try and respond to all the DMs that I get, well, serious DMs that I get. So people can ask me short questions there on Instagram. Or there is a contact thing on my website that does end up in my email, but Instagram is probably the easiest way to get hold of me.
Brilliant. Well, Tommy, thanks so much for joining in today. It's been a pleasure having you on. It's been packed full of useful info. I know my audience, they're going to love it. So thanks everyone for joining in to yet another episode of the Boost Your Biology podcast. This podcast will be live in possibly maybe 8 to 9 weeks from now. But Tommy, thanks again for coming on the show.
Sure. Thanks for having me. It was great.
Awesome. Cheers.